seem to go to sleep, really, does it? Well, your Chrome. Okay, let's start. All right, so we're back for another workshop, this time about the Punctual language, which is a language that I am making, responding to, I think, a quite different set of sounds and desires and goals than the mini-title language that we just looked at. So you can start using this language Punctual in a standalone way in the browser, although it is also available in S3, by going to https://dktr0.github.io/punctual. Here, I will go there, and then I will copy it in big letters here into the browser so you can see it. It's that URL right there at the top. And you can go there anytime. There's always a very recent version of the language available there. And just like we saw a second ago in S3, you can evaluate code by pressing Shift-Enter. In fact, there's no button for doing it here, so you have to press Shift-Enter. And Punctual was inspired by a way of using SuperCollider that is called JITlib. So some people in the room are probably familiar with this. What you do when you use JITlib in SuperCollider often is you make things like oscillators and filters and noise generators and sample readers, and you connect these things on the fly and disconnect them and make them transform each other. And often it's a little bit like what people do when they're doing modular synthesis. That's one common way of using JITlib anyway. So I wanted to be able to do this kind of programming where you're working with synthesis and you're working with simple synthesis elements and you're connecting them, but without having to install SuperCollider. Wanted to do that in the browser so that people could do it everywhere without installing software. And at the same time, wanted to have a notation that was new and maybe more economical even than the kinds of notations that you see in SuperCollider. And so this is what I've come up with so far. If you load it, you get a page that looks like what I have here. And if you press Shift-Enter, like the instructions encourage you to do, you get that slightly loud sine wave. And those generative visuals. And so we're seeing here, I think, another key characteristic of Punctual, which is that it's a language for sound and a language for graphics simultaneously. And it allows us to do things like listen to sine waves while also using them to generate graphics. That's something I've become interested in. So I'm going to erase everything and press Shift-Enter, and we've now got an empty program which evaluates to darkness and silence. But it's a good starting point for our own thing. So I do encourage people to try this, to try to make these sounds as we go along. So here is a simple Punctual program. And I'm going to talk a little bit about it before I evaluate. So what this program says is that there will be a sine wave whose frequency will be middle C. 60M is a way of saying MIDI note 60, which is about 261 hertz, the frequency. But that's hard to remember, so it's more convenient to use MIDI note numbers. 60 is the middle of the piano, middle C. And then that sine wave, which would be very loud if we listen to it just as it is reduced in level by 20 decibels. So it's made to be quite a bit smaller than the loudest possible sine wave. And then all of that sine wave goodness is sent or routed to the position between the two speakers. So when we evaluate this, we're going to hear a sine wave from both speakers, left and right, It's going to sound like it's center panned. There's our center pan sine wave. If I change center for left, it's going to, after a short delay, it's going to go to the left speaker instead. If I change it for right, it's going to go to the right speaker instead. That's a little bit hard to hear, actually. Pure sine waves are hard to localize. So if you didn't get a clear sensation of that going from left to right, it's because that is very hard to hear. We haven't evolved to spatialize, to localize sine waves, because they're pretty rare in nature. If we don't root it anywhere, well, it seems that, yeah, if we don't root it anywhere, it's the same thing as rooting it to center, so we still hear it. Now, very recently, Punctual has gotten these multi-channel signal capabilities, so I want to highlight those a little bit. Right now, we're hearing that 60 hertz sine wave, reduced in level, rooted to the center. If we put square brackets around the 60M and add another note, what we're going to have is two notes that are going to become two sine waves that are then going to get mixed together and are going to come out the center, and it'll sound like this. Now, the programmers in the room might be annoyed by the repetition of the letter M there. I know I was annoyed by the repetition of the letter M. And yes, we can remove it and put the M just after the square brackets. And this will sound the same, which is really useful if you're typing a lot of these things. While we're here, I'll just mention that working with these pure oscillators and giving them these very exact frequencies from the MIDI note scale can sound a little bit antiseptic or too clean. And a cheap trick that everyone does it, so don't feel bad, to make it sound less antiseptic is just to add other pitches that are very close but not exactly the same. So here, this sounds like this. Very pure, very artificial. But if we add something that's just slightly out of tune with it, so now it starts to beat and pulse and chorus a little bit, it's so much more livable. Like that pure sine wave with just the 60, I think I could only listen to that for about 2 minutes without, feeling ill. But now that we've got two sine waves that are slightly out of tune, I think I could probably listen to this for like 3 hours and be happy. Not sure if everyone feels as positive about that as me, but we can do math on these things. So if I put I'm going to put that in brackets, and I'm going to use this to convert those frequencies, those MIDI notes into frequencies instead. And I'm going to put that in brackets, and now I'm going to do +3. And so what's going to happen is that the 60 and the 60.02, they're both going to get 3 added to them. So they're going to become 63 and 63.02. Then those are going to be converted to frequencies. Those are going to become sine waves. And we're going to hear everything shift up 3 semitones. When I evaluate, I get that. So we've seen a couple things so far. We've seen that Punctual has different outputs, left, right, center, that we can direct sound to. We've seen that we can multiply signals by values in decibels. They don't have to be in decibels, but it's a good way of thinking about things in order to make them smaller and not blow our ears out. We've seen that we can make sine waves and that we can make multiple sine waves at the same time with this multi-channel notation, which we can also do math on to shift around. Here, I'm going to make a chord, just to demonstrate that one more time. I'm going to make a chord, put a little bit of out-of-tuneness in it so it's listenable. This is going to sound like this. And then if I move it around, I'm almost making music. But actually, the example I have here now is good for what I want to show you next. So another thing that Punctual has, which it is basically copying from GitLib in SuperCollider with some modifications, is ways of specifying transitions between things that are smooth. So at the beginning of the line, if I put in angle brackets a time, like 10 seconds, what I am saying is when I evaluate this, make the old and the new ones crossfade for 10 seconds. So I'm going to change this to 12, and I'm going to evaluate, and it's going to take 10 seconds. And in the middle of those 10 seconds, we're going to be hearing both the old and the new, which is pleasant. Because I can make music just by moving slowly through different chords and enjoying the interference patterns, the acoustic interference patterns, the pitch interference patterns that I experience as we go through that transition. And if I want to fade away to nothing, what I can do is just take everything that's in between the crossfade and the output specification and erase it. And if nothing at all, no typing at all, is actually equivalent to a silent graph, like a silent set of connections. So this is a totally valid program that makes no sound at all. And so when we crossfade between the old one and this one, what we'll get is like a fade out, basically. Here I'm going to evaluate. And over 10 seconds, the sound will fade away. Okay, graphics. Let's start over again, basically, but do the same thing, but to make graphics. I'm going to make a very simple graphics patch. There we go. There's my first Punctual graphics program. And when I evaluate that, the whole screen turns red. Because what I have said is for every pixel on the screen, the redness should be maximum, or 1. If I make it 0.5 instead and evaluate that, it's going to be not as red. If I put a semicolon and put 1 to green, we're going to get a mixture of green and red, which is pretty green. Fluorescent green, I guess I would call that. So every pixel is getting the same color. So what's happening here is that what's called a fragment shader is running. A fragment shader is one of the parts of the sophisticated 3D graphics systems that we have on so many of our contemporary computers. And the fragment shader is normally, like for example in 3D games, it's the little piece of software that runs on the graphics card that is called upon to shade the surface of objects and make them look realistic or pretty or whatever it is supposed to be happening. It's responsible for that surface painting of each object. Now what we have in Punctual is, we don't realize it, but we have a cube in front of us, or a square. And what we're doing is we're programming a fragment shader that is responsible for painting in that cube, right? And what happens is lots of little programs all run at the same time on each fragment of this cube. Strictly speaking, we don't know how many of them there are. The graphics hardware and system takes care of that. But there are lots of them, and they're all running at the same time to produce color values for each part of this square or rectangle that we're looking at. So when we write a program like the one we have here, we're just saying all of these little programs should set the red value to 0.5 and the green value to 1. I'm going to do this instead now. Instead of, I'm going to write this program, and I get this result. And now what we see is it's black on the left side of the screen, and as we go to the right, it gets redder. So we're seeing different colors at each pixel. fx in Punctual is translated to the current x position. So fx is like how left-right you are, how far to the right you are. -1 is the far left, and 1 is the far right. So fx over here on the left of the screen is -1, and fx over here is 1. And when we apply that to the red channel, we get something that is black for a long time, and then about halfway through starts to go up from 0 to 1, starts to go from 0 redness to 100% redness. If we wanted to stretch this so that that transition from black to red goes over the whole screen, we just have to apply the function unipolar to it. Let me explain that a little bit. In Punctual, we have basically two kinds of signals. We have signals that go from 0 to 1. For example, a color goes from 0 to 1. 0 is none of that color, and 1 is maximum of that color. But a sine wave, or a sound, goes up and down around a rest position. So that's a bipolar signal. It goes from 1 to -1 instead. Frequently, we want to use these things interchangeably, so there are functions for going back and forth between them. Unipolar takes a bipolar signal, gives you a unipolar signal. You may be guessing, bipolar does the opposite. Bipolar expects a unipolar signal, but gives you a bipolar signal. So when we evaluate this, now the red is going to stretch out, because our fx, our x position, which goes from -1 to 1, is now getting mapped on to the range 0 to 1, the range of the red color channel. I'm going to do the same thing for fy, and I'm going to map that onto green. And what we're going to see is an image that gets greener as we get higher. And now we've got a pretty gradient with different colors in the four corners of the screen. Well, where this gets fun, I think, is when we start to use the same things for audio, that we start to use those same things for graphics as well. So let's start simple again. So I'm going to go back to a blank screen. If I take a sine wave at 2 hertz, that'll be something that goes up and down 2 times per second. And if I apply it to red, we'll get a kind of flickering as twice per second. Everything gets red and black. If I could make this unipolar, so it'll be a bit redder. We won't be spending as long in the dark zone of the sine wave. There we go. It's a bit more present now. But it's the same for every pixel. So we can start to experiment with patterns like this. What if instead of the sine wave frequency being 2, what if the frequency of the sine wave depended upon where you were in the image? It's a bit of a trippy idea, I know, but let's try it. We get a pattern of lines that move. Because basically, at every different column of this image, every different x position, there's a different frequency to these sine waves. Moreover, they interact with the projectors in funny ways. So actually, this is kind of fun. Look, because we have 2 projectors here in the room. Look at that projector and look at this projector. And they're different, because these interference patterns play tricks with your eyes and the optics of the projectors and stuff like that. And it looks different on my screen as well. I think my screen is more like what it should look like, and that projector is more like what it should look like. On this projector, something trippy is going on, for sure, because we're seeing these curving patterns that there's no reason in the code that those should be there. some kind of interaction with the optics of this projector, I guess. Yeah, we got some curves over there too, but not on my screen. So one way to start exploring this further is to start to make more complex interference patterns. So if instead of the sine wave depending on the position, we could make it depend on the position squared, we start to get holes in the pattern. I suggest looking at that projector rather than this one. I don't know what this projector is doing. That's more like what it should look like. And if we can do things like multiply the x and the y coordinates together to start to get circular patterns of different kinds. Okay, so there's a lot that we could do further with that. But I want to start again from a slightly different standpoint. So I'm going to go to a blank screen. Commonly when people think about graphics, they think about drawing, like putting this line here or this point here or this rectangle here. And I think that that can be combined with this approach. So in Punctual, there's a function called vline for vertical line. And if you do vline 0 and you send that to the red channel, you'll get a vertical line down the center of the screen. Because again, our concept of geometry here is that -1 is on the left, 1 is on the right. And in terms of the vertical axis, -1 is at the bottom and 1 is at the top. So, you know, the position 1, 1 is like the top right corner, and the position -1, -1 is down here in the bottom left. So we've got a sine wave at 0. We've got a vertical line at 0. If I put a sine wave at 1 hertz here, it's going to go back and forth between 1 and -1, like the eye of the Cylons in Battlestar Galactica. Any Battlestar Galactica fans out there? No. A little part of me just died. But okay, I'll go on. We can do the multi-channel thing with the graphics too. So I'm going to go back to my 0 example. There's my 0. I'm going to put 3 vertical lines by putting a multi-channel signal here. Then we get the 3 lines. And we could put oscillators here too instead. So we could change these to be sine -0.5, 0, sine 0.5. And now we're going to get 2 lines moving in opposite directions. And we can do similar tricks to what we did a second ago. So instead of making it sine and just some frequency, we can make the frequency dependent upon the current x position that is being rendered. So I'm going to put this in brackets, and I'm going to put times f, no, I'll do times fx. And I'm going to do the same thing here. Now we've got kind of like a complex interference pattern. Lots of lines that are being generated. At first glance, it might look random. It's not random. There's a pattern to it. I think your eye starts to pick it out after looking at it for a while. And there are rhythms inside it as well. So we got vertical lines, and how we draw the vertical lines and when we draw the vertical lines is being controlled by this frequency that depends on where we are drawing right now. And again, in case this helps as people are cluing into how this works, we're simultaneously drawing everywhere here. All of these drawing operations are happening at the same time. Our vertical lines are like lined up with our x position, if you think about it, right? That's what a vertical line is. A vertical line is something that has the same x position all the way up and down its length. So we're going to get very different results if we change X for Y here? Because now we have vertical lines whose position depends on their height. And so this is going to make a quite different pattern. It's a bit hard to see. Maybe we have to turn the lights down a little bit. Or maybe it's easier if you just do it on your computers. But now we're getting, these kind of like circular interference patterns. When things are maximally dispersed, they almost look like random dots. But then if you wait a second, they come together as spiral figures. Well, we have H-line as well. So I'm just going to make a similar program with H-line. And I'm going to change the Y's for X's. And I'm going to work with the blue channel instead. So we're going to see simultaneous patterns. Somehow reminds me of spirograph a little bit. Did anyone have a spirograph? Some people are nodding their heads. More people than nodded their heads about Battlestar Galactica. So there's V-line, there's H-line, and there's Rect as well. So I'll show you what Rect does. I'm going to use the green channel. Rect basically lets you tell whether something is inside a certain rectangle. So if we do Rect 0, 0, 0.5, 0.5, and we assign that to the green channel, we'll get a rectangle that is centered at 0, 0, and whose width is 1/4 of the screen, right? Does that make sense? Like, the 0 and the 0 are the X and the Y position of the center. 0.5 is the width, and 0.5 is the height. And it's 1/4 of the screen because our screen goes from -1 to 1. Like, the width of our screen is 2. Right? But now we can start to make these things controlled by oscillators instead. So let's make the X position a simple sine wave. And now it's going to move back and forth like a friendly Cylon eye. Sorry, that was another Battlestar Galactica reference that no one got because you haven't seen Battlestar Galactica. I'm going to make a slightly different frequency for the up and down, and now our rectangle is going to bounce around. Hours and hours of fun there. I'm going to maybe make a triangle wave at a low frequency for the height. And maybe a sawtooth wave, what the hell, for the height. Sorry, the other one was the width. And when these evaluate, it's going to disappear whenever the height and width is negative, and then it's going to reappear. If we wanted to make these heights and widths always positive, we could do that unipolar thing again, right? So unipolar, and then I'm going to put the tri in brackets, and then unipolar, and I'm going to put the saw in brackets. And now our rectangle should be always visible except for a brief moment where it becomes a dot. So, I mean, fun, but I don't want to look at rectangles bouncing around all day. I would just play Pong if I wanted to do that. It's more participatory. This kind of looks like Pong. I think the fun thing to do is to make this interact with the geometry. So instead of having the frequency of our position be always 0.5 hertz, make it be a different rate depending on where we are on the screen. So in brackets, 0.5 times Fy. And I'm going to put the Y position of the rectangle depending on where we are in the x-axis. And I'm going to try that. I don't really know what is going to happen here. Another nice interference pattern, right? One thing I love about these interference patterns is that you get different results depending on when you look. And it can be kind of hard to tell sometimes how long you have to look to have seen the whole pattern. They can be quite long, actually. Especially in this case where we have basically 3 different patterns that we kind of riffed up with slightly different considerations. And they're interacting. And they're mixing in our optical perception. All right, so far so good. So I want to take one final step here before we just play with things for a while, and then spend the last part of the afternoon making some sound and visuals together. And so what I want to do is take that step myself now, make sound and visuals together. So I'm going to go back to a blank screen. And I'm going to start by making a moving line. So I'm going to make a horizontal line, and I'm going to make it a green horizontal line in the center of the screen. And I'm going to do that same crossfade thing that we were doing with the audio so that I can come into this performance elegantly. So over 20 seconds, I'm going to fade this line in. Okay, so we're going to see that line slowly fade in. There it's coming in. And while it's fading in, I'm going to start to do something else. I'm going to start to make a sine wave. So I'm going to make another 20-second fade in for a sine wave at 2 closely related frequencies. And I'm going to make it not so loud, and I'm going to send that to the center channel. We're going to hear that fade in. And now I'm going to make the line start to move. So instead of it being 0, I'm going to make its position sine 0.5. So it's going to take 2 seconds for each cycle of this sine wave. And I'm going to make it a little bit smaller. So it's a subtle change by multiplying it by minus 20 decibels. And we're going to see a fade from that version of the program to the new version of the program. As one line fades in, the other line is going to fade away. And in 20 seconds, we're going to just have the moving line. And we're not going to have the static line anymore. I'm going to change my crossfade on that. And then I'm going to think about how can I make the sine move and the same way. Different ways, right? Different ways I could do this. What if we add another note to our mix? That'll be 60.01, but we'll add to it a unipolar sine wave at the same frequency as our graphics sine wave. So once every 2 seconds. And I'm going to evaluate that. We're crossfading in now. That third note is there. And that third note, it's going to move back and forth between 60.01 and 61.01. So it's going to come in tune and out of tune, in tune and out of tune. And it's going to come in tune and out of tune at the same rate as our line is moving there. So it's interesting to take a moment just to watch for a second and to see if what we see and what we hear, how that works with these two things moving at the same rate. Can we feel that those are related? Do we feel that they're related? I feel like if we look at them, we do. Especially because in the way that we set it up, we took sort of like careful steps to keep things, coherent with each other. Let's do the same thing in another dimension. So I'm going to make a 2-second fade to a vertical line that moves twice as fast as the horizontal line and is in a different color. And at the same time, I'll introduce another sine wave at a different set of frequencies. Similar pattern though. But again, moving faster. And I'll apply that to the center. So we've created a certain kind of synchronized audiovisual phenomenon here by carefully working with low frequency oscillators. The sine 0.5 and the sine 0.1 are both things that oscillate slowly. We're using them to make correspondences between the audio and the visual. One last step I want to make before ending this tutorial is to address one of my pet peeves, which is things that occupy the whole screen. Like, it bugs me right now that these two lines occupy the whole screen. I would like them to be smaller somehow. So there's different ways of doing that. But one way would be to multiply them by a rectangle. So I'm just let me type this out so we can think about it. A few moments ago, we saw something like this, right? And we said that tells you if you're inside that rectangle. So I want to say in a little bit more detail how that works. Rect 0, 0, 0.5, 0.5 is a function that gives you the number 1 if the currently drawn fragment is inside that rectangle, and it gives you a 0 otherwise. But the thing I want to emphasize here is it gives you a 1 or a 0. If you multiply something by 1, you get that thing. If you multiply something by 0, you get nothing, right? So we can multiply our graphics expressions by that rectangle to kind of window it, to make it only appear at a certain place. So here's our green line. So I'm going to make that multiplied by rect 0, 0, 0.5, 0.5. And I'm going to do the same thing for our red line. And I'm going to do a long fade, 20 seconds on those things, so we get the thing slowly coming down to the more constrained image. I hope. It's new software, so I'm always like afraid that stuff's just not going to work. Oh, it's not working because of my mistake. I left this code here at the bottom, which made the whole thing not work. Okay, second attempt. Now we have our more constrained image, which makes me so much more happy than when it was occupying the whole screen. I think this is maybe just a cyclical thing. I think I've been to so many events where the graphics are just like full-on, like pulsating walls of color all the time, that I'm ready for things to be more minimal. Probably if you come back to me in 10 years, I'll be like pushing for pulsating walls of graphics instead.
Everything
But
small again.
yeah, exactly. Right now I like things that are small. Yeah. We could move this down a little bit. Let's make that change. I'm going to change the crossfade to 5, and I'm going to just make this minus 0.5. No, we'll keep that at 0, the center of the screen, but lower down. Oh, I didn't change this one. Whoops. So I got to change this one too. And we've lost our horizontal line because we're windowing below where the line was. We should move the line as well. So how do I move this? This line was centered on 0. And now it's still centered on 0, but we're windowing somewhere else. We're windowing minus 0.5 down. So we can just, whoops, I accidentally did it back. Well, I guess that ends that. That was a good place to end. I still hear little spectral echoes of the code from other people's computers. That's cool. Anyway, so I think there are a few more little tricks built into it, but I think those are the main things. So I think now we should start to play with it for a little bit, and then maybe see if we can play with it together as a live coding roulette.